Hello and welcome to Empowered Learning. This particular lesson will be on what we call the composition of functions. And so when we say the composition of functions, what we actually mean is that we want to take a function and what we say stuff it into another function. Put another way, we're looking at a function where its independent variable or its quote-unquote x value is also a function itself. So we're going to take a look at these, what they are, how we put them together, as well as evaluating them at a particular x value or substituting an x value for a number. And we want to find the domain of these particular type functions as well. So let's go ahead and get started. So we see we have our composition function in shorthand notation written like this. And notice that this is an open circle here. And we read this as f of g of x. And so if we write it in its more literal form, we see f of g of x, where the g of x is what we call our inside function, which is acting as our x value for the function. And then our f of x is acting as the outside function. Okay? And so that's pretty much all there is to the actual function itself. What we're going to do here is look at these particular functions here, given these original functions here, and we're going to figure out what these are as well as what their respective domains are. All right, so let's go ahead and get started here. So we see that f of x is a linear function, 3x plus 2. G of x is a quadratic function, 2x squared minus 1. H of x is a square root function, and z of x is our quintessential rational function, 1 over x. Okay, so first we see we have f of g of x. We want to form what that is. So we come and rewrite it in its more literal form, like here. And we notice that since f is the outside function, we look at f, and whatever we see, wherever we see x here, we're going to go ahead and replace that with g of x. So we would write this as 3 times g of x plus 2, because everywhere where x is, remember x is just a placeholder, we're now plugging in the function g of x. Okay, so we come here and we know that g of x is just 2x squared minus 1. So we plug in 2x squared minus 1. Don't forget our plus 2 at the end here. And then from there, we will go ahead and simplify. So we distribute, and we have 6x squared minus 3x plus 2, and that ends up giving us 6x squared minus 1. So that is what our first function is. We'll go ahead and move on to the second one now. So this time we see instead of having f of g of x, we have now g of f of x. And remember, this is an open circle and is not read or written as golf of x, okay? So if we come here and we see that our independent variable is now the function f of x. So we look at our outside function g of x, and wherever we see x, we're going to replace that now with f of x. So we have 2 times f of x squared minus 1. And so now we're going to go ahead and stuff in f of x. So if we come here, this will be 2 times our f of x is 3x plus 2 squared minus 1. Okay, and so then from this point, what we'll do is simplify. So here we see that since we have multiplication here and we have this the 3x plus 2 squared, and we have the 2 in the exponent, we have to do the exponent first. So that means we have to FOIL this out. And so if we FOIL it out, we will get, I'll do this the long way, make sure that it's clear for everyone. This actually means this. And so when we do this next step, we know that we get 6x squared. And so Here we would have 2 times 3x, which would be plus 12x, and then we would have plus 4 to end with if we were to FOIL that out. And then of course, minus 1 at the end. Okay? So now we just distribute our 2 to each term. And so this would be 12x squared plus 24x plus 8 minus 1. And to combine like terms some more, we see, I think I got this wrong. This is supposed to be a plus 8. Plus 8 minus 7, so that gives us a positive 7 there as our answer. Okay? Any questions about that? Shouldn't have any. Let's go ahead and move on. So next, we see that now we have z of h of x. So if we look at our function z, it's 1 over x. And if we look at our function h, it's square root of x minus 2. So we're going to take our function z, take h, and plug it in everywhere where we see x. So here we know that this means z of h of x, and this will be 1 over h of x. So this is what we mean by taking h and plugging it in wherever we see x here for z. And finally, we have 1 over square root of x minus 2. Okay? So for our last one here, we have z of f of x. So now function z, function f, so we're going to take f and stuff it into z. So when we do that, we have 1 over f of x, and that gives us 1 over 3x plus 2. Okay? So we see now how to take any two given functions and from that make a composition function from it. So now what I'm going to do is erase all these and just end up with the answer, and then we'll work on the domain for each. And then after that, we'll do one last example. Okay, so now that we have these, we will work on the domains of each. So I'm going to go ahead and switch pen colors here for a second. For A, we see that when we actually plug in the function g into the function f, this is the form that it's in, okay? And so it's important to look at the domain of a composition function from its what I call the raw form of what it looks like as soon as you plug it in. So if we see here, when we plug this in, there's not too much going on as far as what can be violated when looking at the domain of a function. So here we can go ahead and multiply everything out and we get 6x squared minus 1. And we know that this is a form of a polynomial And polynomials, for any polynomial, its domain is all real numbers. So for here, the domain of this one would just be negative infinity to positive infinity, or what we call all real numbers, okay? For the next one, we see that when we plug this in, we have a similar type thing. 3x plus 2 squared is a polynomial, and if you multiply that times 2, it's still a polynomial, and if you add 2 to that result, it's still a polynomial. So for here, the domain again is from negative infinity to positive infinity, or we could just say the set of all real numbers, okay? For this next one here, we see that we have 1 over square root of x minus 2. And so to remind ourselves of, for functions like these, how we figure out what the domain is, there's two things that we don't want to violate. In other words, we're going to look at the domain of the function by trying to figure out what we can't have. And so the first thing that we can't have is we can't have you plug in an x value into the function that makes you end up getting 0 in the denominator of it, okay? And so for here we see that if we plugged in a 2 here, we would have 2 minus 2, which is 0, and square root of 0 is 0. We know that anything divided by 0 is undefined, which means that whatever x value or values make that happen, then we can't have those particular x values in the domain. So from looking at this, seeing that this particular criterion is violated, we know from here that x cannot equal to 2, okay? The other thing that we have to take into account is, and I write it this way for short, and I'll explain what I mean. What this means is we can't plug in an x value into a function that has square root of something, or fourth root of something, or sixth root of something, and it ends up giving us a negative number. In general, what I'm saying here is that if we have an even nth root, which means square root, fourth root, sixth root, eighth root, so on and so forth, if we have that somewhere in our function, we can't plug in x values that make us have negative numbers under that radical, or in the radicand, okay? So here we see that how we limit this is we have to say whatever is in this box here, whatever is in the radicand or under the expression here, it has to be greater than or equal to 0. So knowing that, we have to say that this x minus 2 is going to be greater than or equal to 0, which means that x has to be greater than or equal to 2, okay? So again, looking at our two criteria here, we know we don't want any of these situations here. Anything that makes us divide by 0 when we plug it in, or anything that makes us take the square root, fourth root, sixth root, so on and so forth, of a negative number, whenever we take the even nth root of something, whenever we plug in the x value, and we result in a negative number under the radical, then we can't have that, those particular x values in the domain, okay? So here we see that we have x can't be equal to 2 and x has to be greater than or equal to 2. If you notice, there's a contradiction here with the equal part. So if we bring both of these together, we see that the x values that satisfy both this and this at the same time will be x is greater than 2. So x is greater than 2 would be our domain. If we express that in interval notation, it would look like this. Okay? And now for the last one here. We see that we have z of f of x, and this is how it is when we plug in the f of x into the function. And notice here that we have value of x here in the denominator, and there may be a number here that if we plug it in, we will possibly get 0 in the denominator. So to figure that out, we say that we know that this particular expression can't equal 0. And if we go ahead and solve for what that would be, we will quickly see that the value of x that we can't have would be a negative 2/3. We can have any other x value, just not negative 2/3. So here, the domain for this last one would be all reals except for negative 2/3. And if we write this in interval notation, it would look this way. Okay? All right, so next, I'm going to erase all of this and put one last example up to show you how we could take two functions, form composition functions from them, as well as figure out what the domain of those functions would be. Okay, so next what we're going to do is, now that we know what our functions f of g, g of f, z of h, and z of f are, we're going to take these and plug in particular values of x into them. Okay, so if we start off here, we know that we have g of f of g of 2. And so that actually means this. Now there's two different ways you could actually go about doing this particular function here. One way, which I'm going to show you now, is we can figure out what f of g of x is, which we've done here previously in this video, and then from that we can just plug in the x value. So this is one way. So we come, plug in the 2, and then we know 2 squared is 4. This is 24, so our answer is 23. Okay, so that's one way. Another way that we can do this is we can actually use our function f and g here, figure out what g of 2 is first, and then after we figure out what g of 2 is, we take that number and we plug it into f. So I'm going to go ahead and do that now. So up here, I'm going to go ahead and do this. So let's say we want to know what g of 2 is first. So we know that g of x is just 2x squared minus 1. So we plug in 2 into there. And we see that we get a result of 7. And so therefore, f of g of 2, we would just take our 7 now and plug that into f here. Okay? And so when we do that, we see that we have 3 times 7 plus 2. 3 times 7 is 21. And 21 plus 2 is 23. So you see that we can get this either way. Okay? So the rest of these examples, I'm just going to use my function z of h and z of f, since I've already know what the final function is. But just want to let you know, you can approach it this way as well, by doing them separately. So our z of h of 5, we know we just plug in 5. And so we have 1 over square root of 3. And of course, if you want to rationalize the denominator, you could go ahead and do that. And square root of 3 times itself just gives you 3. So this answer, or this answer, is acceptable. It just depends upon which instructor, or what your instructor prefers. Okay. All right, and so for here, z of f, we know that's 1 over 3x plus 2, and we'll just plug in a 4 here. And so if we tally up what the denominator is, we'll see that that's just 14, so our answer is just 1/14. Okay? So now we've talked about forming composition functions. We've also talked about taking the composition function and evaluating it at a particular x value. So the next thing that we're going to do now is actually going to we've also found the domains form as well. So the next thing that we're going to do is do one more example where we take a function f, take a function g, and form composition functions going both ways with them, meaning f of g of x and g of f of x. And then afterwards, we'll find out what the domain of those functions are. Finally, we have our two functions f here. I mean, you see I've changed it. X minus 2 divided by 4x and we have another rational function g of x, which is negative 2 divided by 4x minus 1. Okay, so if we look here, I want to first form what f of g of x is, and then afterwards I want to form what g of f of x is. So we're going to form both of these functions and then from that figure out what its domain is. So let's go ahead and start with the f of g of x first. So we know that this means f of g of x, literally written that way. And so that means everywhere where we see x here for f, we are going to plug in g for that. So if we do that, that would be g of x minus 2 divided by 4 times g of x. And let me get this looking a little better. Okay, and so now we know that g of x is a negative 2 divided by 4x minus 1. All that minus 2 over 4 times negative 2 times 4x minus 1. And so from here, what we need to do is just simplify as much as we can. We see that both in the numerator and denominator, we have fractions. And so we have fractions within fractions here. And the way to sort of simplify this is take the LCD of all the fractions. Well, both of the fractions have the same denominator, 4x minus 1. So what we could do here is multiply this particular complex fraction by 1, but write 1 as 4x minus 1 divided by 4x minus 1. Okay, so in doing that, come here now, we have to distribute 4x minus 1 to both terms here. And when we do that, our first term ends up looking like this in the numerator, and our second term looks like this in the numerator. And then we take that and then divide it by what we have here. So since all of this is multiplication, unlike what we see here, all this can be multiplied times each other. So we have 4 times negative 2 divided by 4x minus 1, all that times 4x minus 1. Okay? And so I'm going to put this over 1 here, because at this point we know that for our denominator, these 4x minus 1s will reduce to 1, because it's just like saying 4x minus 1 divided by itself. So these reduce to 1, and we see in our denominator all that we have left is, if we put that over 1, 4 times negative 2 times 1, which is a negative 8, all over 1, and we know that result is a negative 8. Okay? In our numerator here, we see that we have 4x minus 1 divided by 4x minus 1 again. So that reduces to 1. And we just have a negative 2 for the first term. And if we distribute our negative 2 for the second term, we end up having a negative 8x plus 2. And so in our next step, we see that we have negative 2 plus 2, which cancels to 0. And we have a negative 8x over negative 8. And of course, the negative 8s, they reduce to 1 as well. And our final answer just ends up being x. Okay? So we see here that for f of g of x, if we were to actually write everything out, f of g of x, when we plug it in, plug in g of x into it, it will look like this to begin with. And then the final result ends up being just x. Okay? And so this part is going to be important later on as we look into the domain of the function here in just a second. All right, so we have what f of g of x is. Let's look to see what g of f of x is. So we see that we have g of f of x. So now we're going to take f and stuff it into g everywhere we see x in the function g. So if we look here, this will be -2 divided by 4 times f of x minus 1. Okay? And so now we're going to actually write explicitly what f of x is. And f of x, we know, is going to be x minus 2 divided by 4x minus 1. And so from here, we see that there's really nothing to do with the numerator because we just have a -2 there. However, we see here we have 4 times x minus 2 divided by 4x. If we take this 4 and put it as 4 over 1, we see that this 4 and that 4 will end up reducing to 1. So we end up having in our denominator now x minus 2 all over x and then the minus 1 appended onto the end of that. Okay? So from this point here, we see that we have a complex fraction, and to make life simple for ourselves, what we can do is multiply numerator and denominator by the LCD of the fraction, which is just x. So if we do that, we have a minus 2x here, and here we have to distribute both terms. So I'm going to rewrite this for clarity. This times x, and then minus 1 times x. So if we distribute the x to both terms, that's what it would look like. Of course, this x here could go over 1, and it reduces these two x's to 1. And we just have x minus 2 here. And then, of course, a -1 times x is just a minus x. And x minus x cancels to 0. And we have a -2x minus 2. And that gives us x again. Okay? So for our function g of f of x, when we stuff the function in, we end up having, I'm going to use this form of it here because it's a cleaner form of that, but it doesn't change the properties of it. So we have this, and when we simplify that, we just got x. Okay? So now what we're going to do is, now that we see that the function f of g of x and g of f of x appear to be the same exact function, we're going to show by finding the domain of f of g of x and g of f of x that they are actually different. Okay? So starting with f of g of x, we notice here that in finding the domain, we want to make sure that we don't violate those two things that we talked about earlier. And just to repeat, we do not want to plug in an x value that makes us end up having to divide by 0 after we plug in that particular x value. If we have an x value that does this, then we know that that particular x value or values are not in the domain of that function. We also do not want to plug in an x value into a function that has a square root, a fourth root, a sixth root, and we have to plug in an x value somewhere under the radical there, and we end up having a negative number under the radical or in the radicand as a result. So if we have an x value or values that will do that, we exclude those from the domain as well. Okay? Now looking at f of g and g of f, we see that we don't have this issue to contend with because none of these have square roots in them or fourth roots, sixth roots, etc. So we can go ahead and get rid of this one. However, we do see a lot of this going on, okay? Or at least a possibility for it. So we're going to stake out where that may be, and from that, figure out what our restrictions are, and then from that, figure out what the domain of those particular functions could be. So for our function f of g, we see that this is where we have a denominator. This is where we have a denominator. And here is where we have a denominator. Okay? So for starters, we're going to take, of course, here and here are going to be the same denominator, so we don't have to look at them twice. So in all actuality, we can just say these two denominators are what we're going to consider. And so what we know here is that the denominator can't equal to 0. So we can't have 4x minus 1 equaling 0. And we also can't have 4 times negative 2 divided by 4x minus 1 equaling 0 as well. So I'm going to go ahead and multiply the 4 times the negative 2, and that's going to give me a negative 8 over 4x minus 1 cannot be 0. Okay? So when we do this, here's what we're looking for. If we actually solve this for x and we get an actual number, so for instance, if we have x is not equal to, and then we actually get a number on the other side, then we know that, hey, there is a number or numbers that cannot be used in the domain of that function. If we get something like 2 is not equal to 5, then of course we know that, but that's communicating to us that there is no x value that will make the particular expression on the left equal to 0. Okay? So in solving this, we'll add 1 to both sides. And then from here, divide both sides by 4. And we see that x is not allowed to be 1/4. Okay? So we know that for starters here, x cannot be 1/4. All real numbers except for that. If we come here and try to solve this, of course, we can start off by trying to do this. And this is assuming that you can plug in 0 into here and that x will not be 1/4. So assuming that, hey, you're not using this number here, we're going to go ahead and do that. And we'll have 4x minus 1. Ooh, that's looking a little crazy here. So I'll just make some separation. 4x minus 1. And so here we know that these two 4x minus 1s reduce to 1, and 0 times anything is 0. And you see that we have a negative 8 is not equal to 0, which is a true statement. But what this is communicating to us is that there is no x value that will make the expression 4 times negative 2 divided by 4x minus 1 equals 0. So from this, we see that the domain of our function is just all real numbers except for 1/4 here. And in interval notation, it looks like this. So I will just note here for short that x cannot be 1/4 here. And then we'll go on into find out what the domain of g of f of x is. Now for g of f of x, we see here that we have this whole denominator and we have this denominator. So we see that the x minus 2 divided by x minus 1, all of that can't be equal to 0. And in addition to that, we know that x itself cannot be equal to 0 because it's in the denominator by itself here. So if we look here and here, we're going to get what values of x can't be in the denominator if we can solve it. So if we look here, we can add 1 to both sides. And we have this. And of course, we can write 1 is just 1 over 1. And now this is a proportion, so we could cross multiply. And we have this situation here. And so from here, if we subtract x from both sides, you see that we have 0 equals, well, not equal rather, because we're trying to follow what's up here. We have 0 here and -2 not equaling 0, which is a true statement, but this is communicating to us that there is no x value that's a real number that we can plug in to make this whole entire denominator 0. Okay? So for g of f of x, we know that our domain is going to be all real numbers except for at x equals 0. Okay? So now we see that g of f of x and g of f of x and f of g of x, they appear to be the same by both of them equaling x, but you see their domains are different. And so what I'm going to do to conclude this particular lesson is to draw you what f of g of x looks like and what g of f of x looks like so that you can see that the functions are indeed different. Okay? So for our function f of g of x, if we were to draw this, we know that it looks like, let's say, the function y equals x, but at x equals 1/4, it won't be defined, or it's not in a domain, so there will be a hole there. Okay? So if I was drawing this function, y equals x just looks like a line with a slope of 1. But when I get to 1/4 here, of course, this would be 1/4 for the y coordinate as well. There would be a hole there. Okay? Now for g of f of x, we would draw same line, but now we know that x can't be 0, so right here in the middle, we would have to have a hole. And so a line with a hole when x is at 1/4 and a line with a hole when x is at 0 are two very different things. And so hence why these two functions, even though they appear to look the same, their domains are different. And that's one of the important things that we have to distinguish whenever we're talking about the composition of functions.